All right, let's see how we're doing. So as I said, the equations. So what would the pH of ammonium chloride? So ammonium chloride is NH4Cl. That's a salt. So with a salt, we are going to dissolve it in water. So we're not adding water as a reactant because we're not reacting with water like we are in the other equations. We're simply dissolving it, a solid, into an aqueous solution to make this particular solution. So when it is dissolved, we have NH4 plus and we have Cl minus. And since this is 0.20 molar, and there's only one of each, this is 0.20 and this is 0.20. So we can do stoichiometry at this point. Okay, so now out of that, now we have to decide which of these two right here are going to affect pH. Well, NH4OH is going to be the parent acid or the parent base, or you could recognize that it's ammonia, one or the other, either one. Because remember, if you put this was one of our products that if we had that exist in water, it gives you NH3 and H2O, if you remember, it decomposes. So either one of those, whoa, that is a big eraser. So NH4OH or NH3, but that is definitely a weak base. And then we have HCl, which is a strong acid. So Cl minus is going to be the conjugate base from the strong acid HCl, which means it's not going to have an effect on the pH. We take the other ion and we carry that down and we do our second set of equations, which this time it is a reaction and it is equilibrium. Ammonia, NH4 plus is going to act as an acid and donate its H plus. So anyone that's positive is going to donate an H plus. Anyone that's negative is going to accept an H plus. So water can act as the water or the base. In this case, it's accepting the H plus and you get H3O plus. So it's water is acting as a base and there's its conjugate acid. And then NH3 or NH4 plus would produce NH3, conjugate acid base, or acid forming a conjugate base, acid base pairs. All right, now we have an ice chart. We have equilibrium. So this will always be the same process. Dissolve the salt, figure out which ion affects pH, and then do the reaction with that ion. We're starting with 0.20 molar. So we got that right from here, our initial concentration. We don't have any of this or any of this yet. It's always going to be minus X. It's always plus X and plus X. The ratio is always 1 to 1 to 1 to 1 in these because you always lose one hydrogen at a time. I will eventually show you one where you lose two. All right, so now I can write the K expression. So the Ka expression, Ka, well, we have H3O plus. If it's OH minus, it's Kb. And we have there our Ka expression. So now we're always given a value up here in the problem, but it's always going to be of the base that produces the conjugate acid that affects the pH, or the acid that the conjugate base that affects the pH. In this case, it's the Kb, and it's 1.8 times 10 to the minus 5. So the Kb for NH3 is 1.8 times 10 to the minus 5. The equation is Kw equals K, and that is on our equation sheet. It was the other value or the other equation involving Kw. All right, we need a Ka. As I said, we need Ka because we have H3O plus. And we will get the Ka. Notice how small the Ka is going to be too of the weak base. So the base was small. It was 1 times 10 to the minus 5, but its conjugate acid is even smaller. It's 5.6 times 10 to the minus 10. So 5.6 times 10 to the minus 10 equals X times X over 0.2 minus X. We're going to ignore the minus X, and that's definitely going to be valid, although we will check the percent ionization just to show it. But I mean, it's times 10 to the minus 10 compared to times 10 to the minus 1. So I've been talking about those, the difference in order of magnitude. So 5.6 times 10 to the minus 10, oops, and then times 0.2. That's equal to x squared. Take the square root. And we got 1.06 times 10 to the minus 5. So x equals H3O plus, which now all I have to do is the negative log. So the negative log of 1.06 times 10 to the minus 5 will equal the pH. This is the molarity of the H3O plus. So you can see it's going to be, again, if we're estimating, if it was 1 times 10 to the minus 5, the pH would be 5. So we know it's going to be a little less than 5. Negative log, and we get 4.98. pH is 4.98. Notice it's a acidic pH. And we would have predicted that based on the formula. So if we go back to just having the formula, if I were looking at this, it comes down to, what is it formed from? It's formed from a strong acid and a weak base. And so we know that it's going to be acidic, and due to the conjugates. I said I would do the percent ionization. So the percent ionization, remember, is always what you got for X over the initial concentration times 100. So 1.06 times 10 to the minus 5 over 0.2 times 100. So 1.06 times 10 to the minus 5 divided by 0.2 times 100. And this thing is 0.005% ionized. So, crazy small number. But times 10 to the minus 10, it's what we expected. All right, so that was the first one. Let me do the second one. Let me just get rid of all my work here. Now we're calculating the pH of a 0.5 molar solution of KCN. The process is exactly the same. First, dissolve it in water. How do we know it's going to be soluble? Good question for you. I mean, the AP test is coming up. We're going to be doing lots of review before then. But we know it's going to be soluble because it's potassium, group 1 solids. So we get K plus and we get Cn minus. All right, so out of those two, which one is going to affect pH? Well, K plus came from KOH, HCN came from, or Cn minus came from HCN. This is a strong base, weak acid. How do I know that's a weak acid? Well, it doesn't have 2 more O's than H's, and it's not HCl, HBr, or HI. So this is the one that's going to affect the pH, not K plus. The concentration was 0.5 molar. So this was 0.5 and this was 0.5. That's what we're going to carry down, Cn minus plus water. So our second reaction involves equilibrium. Add it to water. It's negative this time. Last time it was positive, so it gave up an H plus. Obviously, this one can't give up an H plus. It doesn't even have an H plus. So this time water is donating it, and you get HCN. Notice where we are. What's left over then is OH minus. So now we have OH minus, so we need a KB. Notice we're given a KA. Ice chart. Ignore water. Carry down the concentration of 0.5. It's always minus X, 0 and 0 plus X, X and X. We need to write the KB expression. The KB because we have hydroxides. When you have a hydronium, you have a Ka. Very repetitive to these. Now, there's a lot of parts to it, but they're very repetitive as you do more and more of them. Okay, so now we have a Ka. The Ka, according to the reaction up there, is 5.8 times 10 to the minus 10. So we need Kw equals so we got 1.72 we'll save, why not? Okay, so now I can carry that over here. So 1.72 times 10 to the minus 5 equals X times X, X squared over 0.5 minus X. Ignore the minus X. I'll just leave it there, times 0.5 square root. So x equals 0.0029. We'll leave it at that. All right, well, this time it doesn't equal the H3O plus, but instead the OH minus. So don't make that common mistake that I kept referring to, which is when we do the negative log this time, so 2.9 times 10 to the minus 3, you can see it's going to be a little less than 3. Negative log of our answer, you can see we get 2.53. But that is not the pH because it's OH, so 14 minus. And we get 11.46. So we have a leap. Notice it's a basic solution this time. Well, if we refer back to the top, if we wanted to predict just whether this was acidic, basic, or neutral, it's formed from a strong base. And so it has negligible strength on pH, but a weak acid. And so that's going to have a basic pH, its conjugate. Let's do the percent ionization again. So percent ionization, we take X, 0.0029 divided by 0.5, its initial concentration times 100. The meaning of this is if it's greater than 5% ionized, then the minus X that we ignored right here is not a valid assumption. Our answer is going to be way off. It being less than 5% means we can ignore the minus X, save a ton of time with algebra, and still get about the same answer. So what do we got? So 0.0029 divided by 0.5 times 100, and you can see it's still only 0.58% ionized. So 99% not ionized, weak acid or weak base. All right, next one. We have, let me get rid of all my work again. Our salt this time is NaF. How do we know it's going to be soluble? Group 1 again. Sodium ions, fluoride ions. NaOH, strong base, weak acid. Add it to water. It's negative. So now hydrogen is losing again. Another hint is they're giving you a Ka of one of the products, always. We need a Kb. Ice chart, no water. 0.175. Now I didn't do the stoichiometry there. What you have to watch for there is if it's not a 1-to-1 ratio. All of these were. Today it won't be. 0, 0. Minus X. Minus X, plus X, plus X, X, and X. Are we seeing the repetitiveness? Kb this time. OH minus. HF, OH minus, F minus. We need a Kb. I'm not going to write down the work. I'm just going to do it. So we're going to have 1 times 10 to the minus 14 divided by 6.61 times 10 to the minus 4. So the Kb is 1.51 times 10 to the minus 11 equals X squared over 0.175 minus X. Ignore the minus X. I'm not even going to do the percent ionization. Look how far off they are. Times 0.175 square root. 1.63 times 10 to the minus 6 equals X equals the OH minus. So negative log, and we get a pOH of 5.8, 14 minus, we get a pH of 8.2. All right, so those were the 3 tricky ones. The last one was actually pretty simple. Did you figure it out? Well, you saw the answer, right? So our answer, I don't know if I have the answer on my page. All right, so KBr, let's just follow the same process. K plus, Br minus. All right, well, we have KOH and we have HBr. Here's the issue. Strong base, strong acid. So that one doesn't affect and that one doesn't affect the pH. So what affects the pH? What's left? Well, we never really talk about water because we haven't had to. because we had a conjugate that had a appreciable pH strength. Now we do not have one that has a pH strength. So what affects pH is water. So now we just follow the exact same process we just did. We bring it down, add it to water. You get, well, one of them acts as an acid, one acts as a base. We do our ice chart. Now we don't have a concentration of water here, but they're both water. This is 0, this is 0, plus x, x, and x. So I'm not going to do a Ka or a Kb this time because I have both H3O plus and OH minus, and we're doing water this time, so it's a Kw. So it's 1 times 10 to the minus 14 equals x squared. X equals 1 times 10 to the minus 7, which means both of these equal that, which means the pH and the pOH are both 7. So this is a neutral salt. So when you're formed from a strong acid and a strong base, the reason it's neutral, now what we're assuming here is that it's at 25 degrees Celsius. And so the Kw is 1 times 10 to the minus 14. I referred to it on the first day that that reaction, this reaction right here, is actually exothermic. And so it affects, the pH is affected by changes in temperature. Le Chatelier's principle, shifting back and forth. So we'll talk some more about that. All right, so try that worksheet from today. And I will have the answers to that one for you for tomorrow. And then we're going to move on to the next part of this, which is buffer solutions. So buffer solutions are something called a common ion. All right, not any more difficult, but just some more equations.